Inverting operational amplifier. So before going to op-amp operational amplifier, let us see what is an amplifier. This is the input terminal, this is the output terminal. So input, I am going to apply a signal. This is a signal. So I will get a large signal, large amplitude signal in the output. And if it is like this, here the input signal and the output signals are in phase. There is no phase change. This amplifier is known as non-inverting amplifier. Non-inverting amplifier. That means there is no phase change between the input and the output. So if I get the output for the same input, if I get the output like this, these are the outputs, okay? If I get the output like this, then it is a inverting amplifier. This is inverting amplifier. Inverting amplifier. Now we'll see using our op-amp how to make a inverting amplifier and what is its equation for output. An op-amp will have two input terminals. This is the inverting terminal and the non-inverting terminals. A non-inverting amplifier means we are giving the input at the inverting terminal of the op-amp. This let it be the R1. And all amplifiers should have a feedback. So this is the feedback resistor. This is, we'll call it as RF. And here we'll get the output voltage. And what about our non-inverting terminal? This has to be connected to ground. So here we'll apply the V in. This is our input voltage. Now we have to find what is V out. How do we find this? Using the KCL, we'll find what is V out. Now at this node, I will apply KCL. At this node, let us assume the voltage is Vx. Now, what is the current flowing through this R1 resistor? We'll take it as I in. This is an incoming current. This current comes to this node, and one part of this will go to the op-amp here, and the other part goes to, the remaining current goes to this RF resistor. Let that be IF current. Now we know that input impedance of an op-amp is infinity. Here it has got an infinite input resistance. So there is no current will flow into the input terminal of an op-amp. So I equal to 0. I becomes 0. And now as per the virtual ground, what is this non-inverting terminal is connected to 0 volt. As per the virtual ground concept, the 0 volt has to be here at this point also. I hope all of you know that. Otherwise, please watch my virtual ground concept video. So due to virtual ground concept, this node is at 0 volt. Now we'll apply the Kirchhoff's current law. So what is the incoming current? That is I in. I in is the incoming current, which is equal to sum of outgoing currents, IF plus I. I is the current which flows into the op-amp, that we know, that is 0. So I in equals IF. what is I in? How do you find this I in? We are to apply Ohm's law here. As per Ohm's law, V in minus Vx upon R1 equals what is IF? What is IF? IF also similarly, see, current is flowing from this Vx, this node to output. So first we'll write Vx minus V out upon what? RF. Okay, now what we know? Now how do you simplify? This Vx we know it is 0 due to the virtual ground. So we can write it as V in upon R1. Why? Because Vx equal to 0. So here what will equal? Vx becomes 0 minus of V out upon RF. Now what we need? What is the output voltage? That's what we want. So V out, if I rearrange the equation, what I get? Minus of RF upon R1 multiplied by whatever the voltage, input voltage, that is V in, whatever the signal. So this is the output equation. So at the node we have applied KCL, and you should know that the op-amp input terminal doesn't draw current because it's a very high impedance, and due to virtual ground, the both of the inverting and non-inverting terminal will always try to maintain the same voltage. Okay, so I hope these videos are useful to you. Thanks for watching.